Hey friends, Azure HPC Cache is a first of its kind hybrid file system service. It can access data directly from a local data center when running your HPC workloads up in Azure. And by caching your files in Azure, Azure HPC Cache brings the scalability of cloud computing to your existing workflow. Scott is here to show me how it works today on Azure Friday. Hey friends, I'm Scott Hanselman, and it's Azure Friday. I'm here with another great Scott to talk about Azure HPC Cache. How are you, sir?
Doing great, Scott. How are you?
I'm very well, and I'm excited to see the new toys that you have brought me to look at. So let's talk about HPC Cache.
Okay, I'm going to jump in here, talk about a few things, and then we'll jump over and take a look at the service. So the agenda will be, we're going to just do lay the groundwork, talk about some of the data access challenges that brought this service into existence. Then we'll talk a little bit about the details. We'll go over and look at that in the service, and then talk about how to actually get HPC Cache running. So let's start first with the data access challenge. Really, when you think about it, there's a lot of data in the cloud. A lot of data has been moving into Azure, but there's a ton of data that's still located in data centers on premise. In any kind of company, whether you're talking about a life sciences bioinformatics company, or you're talking about an oil and gas concern, or my favorite would be, like a media visual effects company that just did like a movie with animated dogs and whatnot. And all of those assets are sitting in a lot of storage, and that was a lot of money spent. In this particular case, I give you an example of the problem, which is that the amount of data is only growing. And so there is going to be exponential growth in the amount of genomic data being generated. Obviously, with all the circumstances that have been happening lately, I think that's even going to accelerate even faster. And then you look at things like autonomous driving. So it's a little ways off, but the amount of data that they're talking about just collecting in a week is on the order of petabytes of data. And so how do you deal with all of that? Do you put it all in the cloud? How fast can you get into the cloud? And then in some cases, it's sort of like, do you need to put it all in the cloud? And that pivots over to some of these other data points, which is basically, I am the customer. I've done a lot of investment. I have a lot of data sitting in my data center. I'm running all of my enterprise workloads in my data center or in a colo, and I need to make an investment to move to the cloud. What do I do? How much effort do I put into that? Some of those applications could be considered legacy. What are the decisions I have to make? And then basically, a lot of those workloads are looking for a file system. So like we call it network file system, or NFS. And those are typically run on network attached servers or NAS environment. So we have to make decisions about what's going to move into the cloud, what's not going to move into the cloud. And one of the arguments that you could make is, do I have to really move everything into the cloud right away? Can I just get started in the cloud, getting used to running my applications? Let's say I am a visual effects shop in Hollywood, and I'm making, I'm doing frames of a movie. Do I have to put all of the data into the cloud in order to start using Azure Compute, for example? And the answer is no. That's where something like caching comes in. And what caching essentially will do, Scott, is it provides a low latency access for a large number of compute nodes. And I think I should qualify by saying, when we're talking about this HPC cache, the type of target application or target use that you would look at for this is if you're running like a high performance compute cluster, or you're running a render compute cluster, but typically you're running greater than one machine and you're doing a lot of parallel activity, trying to access libraries or trying to access, like I said, with media, I'm rendering a tree. So I have the leaf asset, the bark asset, the tree asset, the grass, and so on. And so all of those things across a large number of machines, we often refer to it as embarrassingly parallel. And so the thing about these types of workloads is that they require very low latency, which is pointed out over here on the left. And they also require a lot of scale out. And so the performance issues with running a compute job in cloud when the data is not necessarily co-located are these four items: latency. So that's how fast can my system respond? Throughput is how much aggregate bandwidth can I generate data across? Scale would be, can I run 1,000 cores, 10,000 cores, 60,000 cores? And then lastly is consistency. And the reason that I highlight this one is a lot of times people will say, okay, I'm going to I'm going to copy or I'm going to sync some of my data up into the cloud. I'm going to run my jobs and then I'll push down things. Well, there's this problem we call write around, which is somebody might still be down in your data center writing data. You've already synced, so you have this sort of disconnect between what's on-prem and what's in the cloud being worked on at the time. And so consistency is also important. All right. And then there's this other issue. This is a little bit esoteric, but there's this thing called metadata. Scott, have you ever, you go into like Windows Explorer and you look at a directory and it has like a date of the file being created and who can access it and what permissions and so on. Those things are called metadata. Other examples of metadata might be I'm a file sitting in a directory, in a directory, in a directory. And so getting all of the information about the path of where that particular file is and its ID, those things are metadata. And they're small and they're expensive because a lot of workflows have to do a lot of directory searches and they have to get information. We call it getting attributes of files in order to run. And this happens at a massive scale, like tens of thousands of operations a second that have to occur. And so one of the challenges is with different types of architectures, you can run into this thing called hotspotting. And hotspotting would be a lot of the machines in your compute cluster all accessing the same attribute or set of attributes about a given file at the same time. And depending on the architectures, which are these three that are spelled out here, depending on the architecture, you could end up really creating instant latency because there's so many requests for it that the machine that has the metadata information gets really busy. And so that's called hotspotting. And HPC Cache is a solution for that type of hotspotting because of the way that it will store all the metadata across the surface of the highly available cache. All right, so what is HPC Cache? Essentially, to frame it up, it is a file system cache. It is designed today for network file system loads, NFS loads. It will be able to show data that's sitting in your on-premise NAS to Azure Compute and allow compute jobs to run. It allows you to even plug into, if you're using an in-cloud, an Azure NAS, such as like Azure NetApp files. For example, let's say you have an ANF volume in a region and you want to run a compute job in another region. You could pop up an HPC cache, point at that volume, and run the job and get the low latency, high throughput that you're looking for. It does allow you to scale out. So it can scale from hundreds of cores up to tens of thousands of cores. We've run production jobs at higher than 65,000 cores, so it can get quite large. The flexibility, I'm going to pause on that one. I'll show you that and the simplicity whenever we go over to the app. So why don't we take a break from slides and take a look over here at the Azure portal. So Scott, are you able to see it?
I am. Looks fantastic. I see that you're looking at an HPC Cache resource group.
All right, awesome. So let's take a look in here. A couple of interesting things. So a lot of times, you can go to the marketplace or you can install an Ubuntu server and you can create like an NFS server and stuff like that. The challenge is always that you are, you're running a machine. You have to care and feed for the machine. It counts against your quota. It's running all the time, etc. HPC Cache is kind of interesting because if you see these four objects right here, so there's an HPC Cache object, then there's these three network interfaces. So those network interfaces are actually the magic. This is a service. So there's a whole team behind this service that's managing and monitoring the state of your HPC cache at any given time. But it has the advantage of these network cards being in your network, you, the customer. And so that means that from a network perspective, this cache can access your data if it's sitting across an express route or across a WAN. It can access it locally, and it can also present it to clients in the subnet here locally for high performance. But the key is also that there is no secret network behind the scenes. This is the only network. And so the team is able to get information through Azure, through our ARM interfaces, and help detect issues or be proactive. But essentially, it's highly secure. It's closed off just to your network, and there's no specific way for us to necessarily get in there. So let's take a look at this Azure HPC Cache instance that's called, it's called VD Bench Cache, but what that really is a utility that runs quite a lot of operations against the machine. And so this is an actual cache. It is running. I'm going to go over just a handful of things. I won't give you the overall tour, but you obviously can stop these. So if you're cost conscious or if you're not running a job at a particular time, a lot of times these media shops or even like a bioinformatics group, they'll run some jobs, but they may not be running 24/7, 365. So this allows you to keep your configuration, stop the cache, and then when you're ready to go, instead of having to reconfigure everything from scratch, you can just start it again and it's ready to start serving ops. A couple of other things would be like cache size. So cache size refers to the amount of disk that this particular cache is servicing. So in this particular case, keep in mind, this is a cache. So this isn't the long-term storage. It's able to serve 12 terabytes of data to your clients, which means that, you can have a fairly large working set. The largest cache that we have will go all the way up to 48 terabytes of storage for the cache. And what that'll then allow you to do is run quite large workloads, large genomic workloads, et cetera. And the key to that cache size is it keeps the data from having to be flushed out and making room for fresh requests of new data. So you can size your cache disks according to what your desired workload is. One other thing I want to point out are these mount addresses. And so typically what we recommend is you might use something like round robin DNS, put some entries in to cycle through these. But these mount points then create a highly available surface. And that's another key about the cache that's different than like setting up your own like NFS server on Ubuntu, is that if there is a failure of one of these addresses, it automatically will take that address and reprogram it so that the cache is always available to clients. It has HA, high availability. And so it will be able to withstand that type of an outage. And the bigger that these caches get, the more resiliency you have built into it. A couple of other things, let's see here. And you can see I was just running some jobs. So this particular cache, I do want to point this out. This particular cache, we sell based on throughput. So you have maximum throughput for this cache of up to 2 gigabytes per second. But I want to point out something about that. If you look at the cache throughput for this, you'll see that it's actually peaking at 5.63 gigabytes per second. The reason that it's doing that.
It's amazing.
Go ahead, Scott.
No, just amazing.
Yeah, and the reason it's doing that.
About things in terms of gigabits. That's just a huge amount.
It's a huge amount. The maximum that we do is up to 8 gigabytes per second today. And if you look at our roadmap, we're going to have some new faster SKUs coming down the line. But the reason that you can get a 2 gigabyte per second cache to do this much more is because it's leveraging the power of machines in the background, storing data in memory. And depending on the type of workload that you have, the low latency responses of that work that's sitting in memory, you'll get very fast responses, sub-millisecond responses for data that happens to be in memory. Does that make sense?
Absolutely.
Okay. So a couple of other things I'm just going to take you through. So how does this thing work? I set up here, there's these addresses. This is what your Linux clients or your Windows clients would mount. So I'll take a quick tour over here. And in fact, this is actually, I was given more time. This is a Nextflow server. It's running some bioinformatic processing. But if I do a quick show of the mount, you'll see that right now I have this particular machine mounted on the HPC cache. And all the data that it's referring to here, even though this is a subdirectory, it's actually aliasing. Let me go to that Avere directory. And you'll see in here is a bunch of genomics data. This particular data is actually sitting in a special blob container that we can leverage as a network attached server as itself. So not only can you point to your on-premise NetApp or your on-premise Isilon or to your ANF volume, but you can also create a blob container that's essentially a file system. So if you need a file system and you want to put some, for example, reference data in here, you can actually do that with blob. But you see these mount points are also then complemented by this thing called storage targets. And so let's talk a little bit about storage targets. This particular cache that you're looking at is pointing actually at an Ubuntu NFS server right now. That NFS server is running at this address. Okay. And essentially you can create a entry for the storage target, point it at the host name, and then you have this thing called usage model. And this is kind of interesting because Scott, a lot of times what will happen, I always like the media guys because they're my favorite. Because who doesn't like The Secret Life of Pets? But like, let's say you're making that scene. A lot of times these guys they'll run render jobs, but then somebody may make a change to the data underneath. That's that write around thing that I talked about. We give you as a customer the control to test the tolerance by checking the modified times of files as you go through. So what this means here, for example, do you see where it says client's right to NFS target bypassing the cache? What that'll do is that'll tell the cache, hey, every time you get this particular file and you have it cached and you're serving it up, let's say we'll put a timer on that particular file. And when that timer fires, I want you, HPC Cache, to go back to the backend storage, that NetApp that's on-prem or that Isilon or whatever, and check the modified time. If it's changed, go get the fresh data and put it in the cache. And so it gives you that kind of control to help minimize the risk of those types of write-around situations so you can feel confident running this in the cloud. Okay, and then you can actually build what's called a namespace. And this namespace is if you go into your client machine and you navigate a directory and you're going through, as I was, let me hear, let's see, data node 2. So as I'm navigating this directory structure is actually on the HPC cache, but it is a virtual directory structure. And what that allows you to do is the HPC cache can point not just at one thing that you have on-prem. It can actually bring together many sources of data. So that let's say you have a NetApp on-prem, and let's say that you have an ANF volume in the cloud. You can actually join them together in a single namespace here, in a single HPC cache, and present that to the client machines as one single directory structure. And so even though they might be navigating around a directory structure, it's actually sourcing data from the two different sources. And you can have up to 10 unique sources of data. And within the unique sources of data, if it's like a NetApp or an Isilon or another NFS thing, you can map all of the exports as one within that restriction. So even though you only have 10, I might have a NetApp with 100 exports on it. I can actually put all 100 in here as namespace targets if I choose to.
What would you say that a good way for someone who's watching this do they know that they have this problem and that HPC cache is what they need? Who's going to be watching and saying, oh, we have to set this up today?
That's a great question. So the people that I talk to the most that have this problem are they're customers of Azure potentially already running many other things. They have a specific set of data that's sitting in their data center, typically around a couple of these verticals that I've been mentioning, but it doesn't have to be. Let's just say it's NFS accessible data. And they have an HPC cluster on-prem, so a compute cluster that they made investments in, but they really want to start doing some of that in the cloud. Whether they're doing it as a complement to their on-prem, which is what we see a lot. Like, I made all this investment, we're going to keep this here, but I need overflow ability. I'm a university, for example. I'm the HPC team in a university. I want to burst extra ability into the cloud. And so I want to take advantage of the compute environment. Well, the problem with that, of course, is I have compute. How do I get the data? And that's where the HPC cache comes in. So anybody that really wants to start running jobs in Azure, whether they're running VMs or they're running containers or they're running whatever, if those things need NFS access to data that they know is on-prem and they just are struggling to find a way to get that data up there, use HPC Cache. You can start doing that in a day. It's very simple to get started. The biggest caveat I would give you is you have to have an express route. Okay. or a decent link.
But as you point out, you could get this going in a day. This could be a project you could put together on a Monday afternoon, and you wake up the next day and the boss loves you, and the whole team is thrilled with your work. So folks can go up to azure.com. They can look for HPC Cache, learn all about it, and sign up.
Yep, right here's the website. I will tell you right now today, the way that we do this is you'll actually, if you're interested in trying this out and you come to the website, you'll fill out a form requesting access. And actually that form will come to myself and one of my coworkers, and we'll be happy to take care of you.
Fantastic. I am learning all about the magic of Azure HPC Cache today on Azure Friday. Hey, thanks for watching this episode of Azure Friday. Now I need you to like it, comment on it, tell your friends, retweet it. Watch more Azure Friday.